Welcome back to Cloudcast, everyone. I want to start today with a story that still makes me cringe. A few years ago, I was consulting for a company running a global gaming platform, and they had users in Tokyo experiencing 280 milliseconds of latency to their servers in Virginia.
Ouch. That's like a quarter-second delay on every action. For gaming, that's basically unplayable.
Exactly. And here's the kicker. They were paying for premium infrastructure. They had fast servers, but their users were taking the scenic route across the internet to reach them. The traffic was bouncing through who knows how many ISP hops, congested peering points, and suboptimal routes.
So the problem wasn't their servers, it was the path users took to get there?
Precisely. And that's exactly what we're diving into today. AWS Global Accelerator, specifically how it uses Anycast IP routing and endpoint health monitoring to solve this exact problem.
I've heard of Global Accelerator, but I'll be honest, I always confused it with CloudFront. They both seem to make things faster globally, right?
That's one of the most common confusions I hear. Let me clear it up right away. CloudFront is a content delivery network. It caches your static content at edge locations. Global Accelerator is fundamentally different. It doesn't cache anything. Instead, it gives you two static Anycast IP addresses that route your users onto the AWS Global Network as quickly as possible.
Okay, so CloudFront is about caching content closer to users, and Global Accelerator is about getting users onto a better network path. But what exactly is an Anycast IP address?
Great question. Let me use an analogy. Imagine you're calling a customer service number, let's say 1-800-Flowers. That single phone number doesn't ring at one specific phone. It routes you to the nearest available call center, maybe one in Dallas if you're in Texas, or one in New Jersey if you're in New York.
So the same number, but different physical destinations based on where you're calling from?
Exactly. Anycast works the same way with IP addresses. When you create a global accelerator, AWS gives you two static IPv4 addresses. Let's say 75.2.60.5 and 99.83.190.102. These same IP addresses are announced from over 100 AWS edge locations worldwide via BGP, that's Border Gateway Protocol defined in RFC 4271.
Wait, how can the same IP address exist in multiple places? Doesn't that break how IP routing works?
It seems counterintuitive, but it's actually leveraging how BGP works. Each edge location announces these IP addresses to their upstream ISPs. When a user in Singapore tries to reach 75.2.60.5, their ISP's routers see multiple paths to that IP and choose the shortest one based on AS path length and other BGP metrics. That typically means the Singapore edge location.
So the internet's routing protocols naturally send users to the closest edge location without any special client-side logic?
Exactly right. And here's where the magic happens. Once traffic hits that Singapore edge location, it's now on the AWS Global Backbone Network. AWS has a private fiber network connecting all their regions and edge locations. Your traffic travels on this optimized, low-latency network instead of bouncing across the public internet.
That's clever. But I want to make sure I understand the limitation of your phone analogy. With a phone call, once you're connected to Dallas, you stay connected to Dallas. Is Anycast the same?
Excellent catch, and this is where the analogy breaks down. With traditional Anycast and UDP traffic, each packet could theoretically route to a different location if network conditions change. This is actually fine for DNS, which is stateless, but for TCP connections, which are stateful, this would be disastrous.
Right. Because TCP needs to maintain a connection state. If my packets suddenly start going to a different edge location, the connection would break.
Precisely. AWS Global Accelerator handles this with what they call flow stickiness. Once a TCP connection is established through a specific edge location, subsequent packets for that flow continue to route to the same edge location. They track this using a combination of source IP, source port, destination IP, destination port, and protocol.
Okay, so Global Accelerator gets my traffic onto the AWS network quickly. But then what? How does it know where to send my traffic from there?
This is where endpoint groups and endpoints come in. When you configure Global Accelerator, you create listeners on specific ports, say port 443 for HTTPS. Each listener has one or more endpoint groups, and each endpoint group is associated with a specific AWS region. Within each endpoint group, you define your actual endpoints.
What can be an endpoint? Just EC2 instances?
Several things actually. You can use application load balancers, network load balancers, EC2 instances with elastic IPs, or even other elastic IP addresses. In the console, you'd navigate to Global Accelerator, create an accelerator, then add listeners, endpoint groups, and endpoints in that hierarchy.
Let me make sure I understand the flow. User in Tokyo hits the Anycast IP, gets routed to the Tokyo edge location, then AWS Backbone carries it to my endpoint group in, say, ES East 1, where it hits my application load balancer?
You've got it. And here's where traffic dials come in. Each endpoint group has a traffic dial setting from 0 to 100%. If you set the US East 1 endpoint group to 50%, only half the traffic destined for that region actually goes there. The rest gets redistributed to other endpoint groups based on their weights and proximity.
That sounds useful for migrations or gradual rollouts. But what happens if my endpoint in US East 1 goes down completely?
And now we're at health monitoring, which is critical. Global Accelerator continuously monitors the health of your endpoints. For application load balancers and network load balancers, it uses the health check status from those load balancers directly. For EC2 instances, you configure health checks specifying the protocol, port, and path.
What are the actual health check parameters? Like how often does it check?
You configure the health check interval, which can be 10 or 30 seconds. You set the threshold count, which is how many consecutive checks must pass or fail before the endpoint is considered healthy or unhealthy. The default is 3. For HTTP and HTTPS health checks, you specify the path, like /health, and the expected response codes.
So if my endpoint fails health checks, traffic automatically routes elsewhere?
Exactly. If all endpoints in an endpoint group fail, traffic automatically fails over to endpoints in other endpoint groups. The failover happens within seconds, not minutes. This is dramatically faster than DNS-based failover, which depends on TDL expiration and client caching behavior.
Speaking of DNS, I've seen people try to do global load balancing with Route 53 latency-based routing. How is this different?
Great comparison. Route 53 latency-based routing works at the DNS level. When a user resolves your domain, Route 53 returns the IP address of the endpoint with the lowest latency. But here's the problem. DNS responses get cached by resolvers, sometimes for longer than your TTL specifies. If an endpoint fails, users might keep hitting the cached bad IP for minutes.
And with Global Accelerator, the IP never changes, so there's no caching problem?
Exactly. Your users always connect to the same Anycast IP addresses. The routing decisions happen at the network layer, not the DNS layer. Failover is nearly instantaneous because you're not waiting for DNS caches to expire.
I want to go back to something. You mentioned the AWS backbone network is faster than the public internet. Do you have actual numbers on that?
AWS publishes case studies showing latency improvements of 20 to 60% depending on the route. The improvement is most dramatic for long-distance routes with poor peering. That Tokyo to Virginia route I mentioned earlier? With Global Accelerator, we got it down from 280 milliseconds to about 160 milliseconds. Still not amazing because physics exists, but a 40% improvement.
What's a common mistake people make when setting up Global Accelerator?
The biggest one I see is forgetting about client IP preservation. By default, when traffic arrives at your endpoint, the source IP is the Global Accelerator edge location, not the original client. If your application needs the real client IP for logging, geolocation, or security, you need to enable client IP preservation, which is only supported for specific endpoint types.
Which endpoint types support it?
Application load balancers and EC2 instances support client IP preservation. Network load balancers with security groups also support it as of late 2023. For ALBs, the client IP appears in the X forwarded for header. For EC2 instances, it's the actual source IP of the packets.
Let me walk through a practical scenario. Say I'm building a real-time collaboration app with users worldwide. I have application load balancers in US East 1, EU West 1, and App Northeast 1. How would I set this up?
Perfect example. You'd create a global accelerator and get your 2 Anycast IPs. Create a listener on port 443. Then create 3 endpoint groups, one for each region. In each endpoint group, add your regional ALB as the endpoint. Configure health checks pointing to your application's health endpoint.
And users automatically get routed to the closest region?
Based on network proximity, yes. A user in Paris would likely route to EU West 1, a user in Tokyo to App Northeast 1. If the EU West 1 ALB fails health checks, Paris users automatically fail over to the next closest healthy endpoint group.
What about the cost? I imagine this isn't free.
There's a fixed hourly charge of $0.025 per accelerator per hour, which works out to about $18 per month. Then there's a data transfer premium based on the dominant AWS region your traffic uses. It ranges from $0.015 to $0.035 per gigabyte depending on the region. For high traffic applications, the cost can add up, but for latency-sensitive applications, it's often worth it.
Let me summarize what I've learned. Global Accelerator gives you two static Anycast IP addresses that are announced from edge locations worldwide. Users automatically route to the nearest edge location via BGP. Traffic then travels on AWS's private backbone to your endpoints. Health monitoring ensures traffic only goes to healthy endpoints, with failover happening in seconds rather than minutes.
Perfect summary. I'd add one more key point. Because the IPs are static, you can whitelist them in firewalls, embed them in IoT devices, or use them anywhere you need stable IP addresses with global reach.
This makes so much more sense now. The phone number analogy really helped, even with its limitations.
That's the goal. Remember, Global Accelerator solves the network path problem, not the content caching problem. If you need both, you might use CloudFront for static assets and Global Accelerator for your API endpoints. They solve different problems and can absolutely coexist.
Thanks for breaking this down. I finally understand why my gaming friends complain about routing and not just server performance.
And that's a wrap for today's episode. Remember, the fastest server in the world doesn't matter if your users are taking the scenic route to get there. Until next time, keep optimizing those network paths.